Okay, so let's continue our lesson on counting from yesterday. Remember, we are left with two problems that we haven't fully gotten the full solution yet. So the first one is the problem about the binary grids, where you have to ensure that the rows and columns all have even number of ones. And the second one is the 3D path problem with walk and fly movements. So let's spend a few minutes to know if anyone has an idea, or at least more insights towards the problems. I haven't seen any new accepted solutions to those problems, so I suppose no one submitted their ideas. So, for example, in the binary grid, any new ideas? So you have some formulas, but I don't think anyone submitted those. So if you remember your formulas, or you can try to derive, if you can derive them again, I suggest you try to submit them before we discuss the full solution. Since there were so few attempts, I don't think I want to discuss the full solution yet until a future session. Okay, so we will leave them unsolved for now, as well as the other problem about paths. If you have ideas, you don't have to tell me during class. You can tell me whenever I'm here. So any insight is great. Okay? So let's proceed. This is a continuation of the lesson that we were having about counting. So let's get back to one of the identities we got earlier. Remember that we have something like this. And we showed that this is true using a double counting argument. The idea behind that can actually be generalized. So if you have something like this, so basically the same idea works. Okay, except this time there are m plus n things. We have to choose r objects. This is just the special case of this for m equals n equals r. Okay? But exactly the same idea works. If you want to choose m plus n objects and you want to, if you have m plus n objects and you want to choose r from them, then you can split the objects first into groups of m and n, and then decide how many you want to take from the first group. And then if you decide k, then r minus k will be from the other group. And then you have this expression, and you just sum for all k that is valid. In this case, it can be from 0 to r. You can also cut the summation short if m or r n is small. Okay, for example, if m is lower than r, you can sum up to m only. Okay? So here's a simpler identity. So this one basically says that the sum of all the numbers in a row of Pascal's triangle is 2 raised to n. And the combinatorial meaning of these numbers is pretty straightforward. You're given n elements, you're counting the number of subsets. And there are 2 raised to n of those, but we can count it in another way. We first fix the size of the subset, and now we want to know how many subsets of size k are there. Well, there are n choose k of those, and then we just sum k from 0 to n. Okay? That's one way of showing this. Another more general version, I guess, is using the binomial theorem. So this one, I want to discuss this. So the binomial theorem states that this expression is equal to this expression. Okay? And you can easily prove this by induction or determining what the coefficient of each of these terms will be using another combinatorial argument. Okay, so let's say you want to know what the coefficient of this number is in this expression. So you're basically choosing how many k x's and n minus k y's from the product, something like this. So if you want to choose k x's, then you have to choose which terms you get the x's from. And then there are n choose k ways to do that. And the remaining one will automatically be y's. And then you will get this term. That's why you get this. Okay, and then summing for all terms, you get this. Okay, and you can easily get this by substituting x and y equal to 1. So this will become 2 raised to n, and this will become just the sum of the binomial coefficients. Okay? We can also prove this identity using a similar idea. Okay? So how do we do that? Let's say we want to compute x plus y raised to m plus n. So let's say I want to know, let's say we set y equals 1. So by this, we get that this is just k from 0 to m plus n choose k, x raised to k. On the other hand, we can also just multiply these separately. What do we get from this? So we will get two sums. Something like this. And then we can multiply them just like polynomials. And then we want to know what the coefficient of x raised to k will be. Or let's say we use a different variable this time, r. So it matches that better. Now, what do we, let's look at all possible values of r. Now, if we want to form x raised to r, you want to ensure that k plus l is equal to r, right? Which means that if we want to loop like this, k is from 0 to m still, but r will become, or l will become r minus k, because we want their sum to be equal to r. But the coefficient of x raised to k in this is m choose k, and the coefficient of r minus k here is n r minus k. So if we do this, then we'll get that the coefficient of x raised to r is this expression, which is equal to this expression because they are the same thing. Okay, so that's another way of proving that. This is not a double counting argument, but this is quite similar to generating function approaches. Okay, so it at least gives you some techniques on how to manipulate things like these. Okay, if you get some generating functions, sometimes you have to do some multiplication like this. Sometimes the result will not be pretty. But sometimes you can just do FFT or something, some fast polynomial multiplication. In this case, we didn't have to do that, where our goal is to prove this. Okay? It all relies on the fact that this is true. Okay? In particular, if you set y is equal to 1, then this is true. So now, let's try to tackle this question. How do we prove that this expression is equal to n times 2 raised to n minus 1? Okay, this is pretty popular as well. What? Okay. So what are we counting here?
All the possible number of teams with like captain is also like there is a special position in the team in a set with a special position in a set.
Okay, so that's one. Another, this is we're counting the number of teams, and then we're choosing a leader for each of those. So if the team size is fixed, then it's just this expression, this one.
All possible.
Yeah, but in this version, we don't fix the size. So we just sum from 0 to n, and then there's another way of counting it, which is to choose the leader first, and then choose the remaining members. Okay? Another interpretation would be, suppose we want to sum all the sizes of all the subsets of a set of n elements. Okay? Clearly, this is this expression. But how do we get this from that interpretation?
Each element lies in different.
There are multiple ways. One is to look at each individual element and count how many sets contain it. So if you look at a particular element, how many sets contain it? 2 raised to n minus 1, because you basically just have to choose the other members. But you have to do that for all elements. So you multiply it by n. Okay? So of course, that's a pretty good interpretation on this number. Depending on the problem, you might encounter sums like this. Okay? So I leave it as an exercise to calculate these sums. Okay? In general, if I set k raised to m, then I want to compute this quickly. Let's say better than O of m squared. Something like that. Okay? Okay, so this is homework. If you have the solution for this, just tell me. Another way to derive this is using algebra. If you can't find the interpretation for both sides, then you can just substitute one of the identities you got earlier, right? And now we can factor n out. And then notice that we can basically remove the case k equals 0 because the term will just be 0 anyway. So we have something like this. And if we adjust variables, something like this, it will just become k, but we already know that this one is already 2 raised to n minus 1. So there's that. Unfortunately, I don't know how much you can reach with this sum. Okay? Next, how about this sum? Can anyone tell me the answer to this? or at least a shorter expression, a closed form expression. Okay, so you're saying 2 raised to n minus 1. And why? Yes.
Summation of NCR is 2 to power n. Now we split that summation into two parts, one containing the odd term and even term. And using the formula NCR is same as n of n minus r, we can show that sum of even part and odd part would be same, and that would be divided by 2.
Okay, so you're describing a proof that uses the Pascal identity, and then looking at the table of numbers. So here we are only summing the even terms. And then if you remember that if we have some triangle, let's say you want to sum these, then this is just the sum of these, and then this is the sum of these, and you'll see that the previous row, everything will be added, right? And we know that the sum of this row is 2 raised to n minus 1. So that's why this is true. Yes? What?
I try to give like one more proof.
Okay.
There is one n% standing aside, and in n minus 1 we take all. We want only even number of combinations of all the n. So if we take a random subset from the n minus 1 left, it is not we add the n%.
Yeah. So yes, there's another combinator proof. This one using double counting. So if you have a set of n elements and you want to know how many subsets of it are even, then first take away one element aside and you're left with n minus 1 elements. And now take some subset of these. It will either be even or odd. If it's even, you have no choice but not add this element. If it is odd, you have no choice but to add this element to make it even. Hence, for every subset of the first n minus 1 elements, there is exactly one subset of n elements that has an even size. That's why we have a formula 2 raised to n minus 1. Yes?
Another way, like we take the expansion of 1 minus 1 whole power n, and then from there you can get that n equals to k, that's sum equal to n equals to k plus 1, that's sum. And since both of them add up to 2 power n, so both of them equal to 2 power n.
You're saying we write this,
So 1 minus 1 whole power n.
this.
Yeah. If we expand it,
Okay, if we do this, we will get 1 raised to k, negative 1 raised to n minus k. We can swap it, so it will be better. Something like this, or something like this. We can do that as well. Now, what is this?
so like that would be 1 if k is even and not if k is odd.
Yes.
Yeah, so from that.
This is minus 1 if it is not odd.
Yeah, so if yeah, so if it's odd, then the terms will be with the negative sign. And then even there is a positive sign, and they both have to add up to 0 because 0 power n is 0. And so we get that those two sums are equal. And now their sum together is 2 power n, you know that. So they will just come.
Okay, that's good. So if k is even, then this will be added. If k is odd, this will be subtracted. And then all in all, they sum up to 0. Therefore, the positive terms will equal the negative terms. But the positive terms are those with even even size. The negative terms are those with odd size. And we know that there are 2 raised to n in total. And they are equal. Therefore, each one is exactly half this. Hence, we get 2 raised to n minus 1 as well. Okay, yes? Yes. Okay, so in the other explanation, let's say we have n elements, and we want to find how many subset of it has an even size. Let's take away one of those elements. Okay, so there are n minus 1 remaining elements, and for each of those subsets, of course, each subset is either of even or odd size. If it's of even size, Of course, we can choose to add this element or not, but there's only one way to do that, so everything becomes even. And the same if this one has an odd size. Okay? Hence, for each subset of the first n1 minus 1 element, there is a subset of the whole thing which has an even size. Is that clear? Okay. So, there are lots of proofs of this. Some algebraic, some double counting. Okay. We can extend this. Of course, if you replace this by only odd terms, this will be n 2 raised to n minus 1 as well. An edge case would be n equals 0, in which case the formula doesn't work. Okay? The argument only works if you can take away one element, right? That's very important. But anyway, if n equals 0, then it's very easy. There's only one subset. It's empty, so it's even. Okay? But just be careful about that. An extension of this is when you are trying to sum something like this. Let's say up to however it takes until it becomes 0. Okay? I'll leave that as homework as well. And now, remember, let's tackle one of the things we did for the problem yesterday about the 3D path. Okay? Remember that the hint I gave you was to look at the destination xy1 and determine how many ways to get to that position. What did we derive? X plus y, choose x minus 1. For this, x plus y, choose x without anything else. Of course, don't assume that the next one will be minus 2 or something. Okay? But why? And then how did we derive this? We have a two-dimensional sum. Does anyone remember? Okay, so something like this. Right? And then somehow we did some crazy trick to collapse the sums so that it becomes something like this. This one is an artifact of adding 1 and then minus 1 so that we can start the collapsing in one of the sums. But why do you think that worked? Okay, it's quite weird though. We expanded it so we can see it. So something like that. This is actually quite a famous identity. If you write the Pascal triangle, so the collapsing thing is equivalent to saying that some element is equal to something like this, the sum of these numbers. Okay, or the other way around. Okay, how can we derive that? Of course, we can use the Pascal identity. This one is the sum of these. But this is the sum of these. And then this is the sum of these. And then this is equal to this. This is just 1. Right? Or you can say this is the sum of these, but this is 0. So the sum of these is equal to this. We can do that the same way on the other direction. So that's why we can collapse the first sum. And then we did the same thing, collapsing the second sum, except we added 1 and minus 1. So it's equivalent to saying that this is equivalent to the sum of this minus 1. Right? So why does that work? We can take this element and then say it's equal to this. And then this is equal to this. This one is equal to this. And then this one is equal to this. Alternatively, you can use the same pattern. This one is equal to the sum of this one. Okay? And then this one is equal to the sum of these ones. Okay? And then you have an extra 1 here. That's why if you add these, you get this minus 1. That's the only reason. You can repeat the pattern. Okay? And it's quite interesting. You can do it from any position. If you get this number, this is just the sum of this plus 1. Okay? So that's why we get that pattern like that. Okay? There's also a combinatorial meaning to that identity. The sum of some diagonal like that is equal to that. Okay? And it's actually called the hockey stick pattern because of the shape of it. Okay? You have a long line and then you turn. So we can write it algebraically something like this. Something like that is equal to. So when we do something like this, we are selecting some diagonal like this and we're adding up to a certain position m. And we want to say that it is equal to this. So this is just m plus 1, which is k plus 1. Okay? This is equivalent to that pattern. Okay? So again, if you have, we want to show that pattern always holds true. And we can write that algebraically as this. This is just some sum like that. Okay? And this is this element. Okay? But how do we prove this? We have proven it using Pascal's identity repeated multiple times. But do you think there's a combinatorial meaning to this? So the most natural one is to look at this. And this is simply the number of ways to choose k plus 1 objects from m plus 1 objects. But can you interpret this sum as the same thing? Let's say you have m plus 1 elements, and you want to choose k plus 1. Why do you think this is also the answer? The intuition behind this sum is probably by looking at k and k plus 1. Remember, we want to choose k plus 1, but in this sum, it seems you're only choosing k. Thus, it seems like we have already chosen some element. Yes?
We choose the rightmost element, take the rightmost element and then choose the other element and iterate.
Yes, exactly. So let's say we want to choose the rightmost element. Let's say it's at position n. Okay, or let's say n plus 1. And then, what happens here? How many... so how can we choose the other elements? We said that this is the last one, so we will not select all the later ones. But we still have to select k elements, and we only have n more elements to choose from. Hence, we get n choose k. Now we simply have to iterate n from 0 to m to complete the proof. Okay? So that's a simple combinatorial argument for this. So now you know at least why that collapsing thing works. Okay? So I guess I'll just add some more things that you can try computing as homework. Here's one. This is not hard. Of course, this is just a practice. Another one would be, let's see. Okay, in this one I have already given you the sum, but you just have to prove. Okay? And then other examples would be okay, this is a simple one. Yes, this is R. Thank you. So this one, this is not hard. But I'll leave two identities that are pretty hard. I'm sure I would guess no one would get this sum unless you search, of course. And I don't expect anyone to get this. And then this one. So to recap, I'm looking for a closed form sum of these. Okay? It's something that there's no sum. Okay? You have some expression, something like this, there's no sum. Or powers is okay, binomials is okay, but sum is not okay. Right? So you have 7, I guess. Yes?
Can we find a close form sum for the top one?
For the top one, this one, I don't think so. Okay? This one is a little different. I'm asking how to compute this faster than m squared. This one's, try to find some closed forms for them. Yes. I want a computation of something faster than this. Maybe. What? In where? Here? Yes. Something that doesn't have a sum. You can use powers, you can use coefficients, but what? Yes, you're right. Okay? Yes? Yeah. Of course, you want to try to find an m squared first. Maybe. Yeah. So you're saying we can just add the terms. That's O of n. But I want something. Yes, I don't want the m factor in the computation. Okay? Of course, the first step is to find something O of n squared, and then try to optimize it somehow.
Pattern maybe differentiating.
Okay. So you're saying some different.
Take 1 plus x power n and keep differentiating. Like do some offsets and keep.
Yeah. Okay, that's possible.
Second one, maybe we can go for cube roots of. First one.
So, where are we differentiating?
We'll take 1 plus x power n.
What?
1 second. Okay, we'll take 1 plus x power n. N.
1 plus x.
N. It's n. 1 plus x power n.
N.
Yes.
Okay, sorry. And then?
So we write its binomial form here. Keep differentiating both the sides.
Okay, so.
Differentiate.
Okay, we differentiate it.
Then multiply an x again. But like differentiation might go lengthy.
Let's say we differentiate it. Okay, so derivative is an operation from calculus. What you do is for every term, let's say you have ax raised to b, you drop the exponent, and then you decrease the exponent. Okay? There's a meaning behind this, but for polynomials, this is basically what you do. So, in this case, let's say you somehow differentiated the left side. In this case, you will differentiate it into something like this. Kx, k minus 1. We drop the exponent.
Multiply an x again both the sides, then again.
Yes, and then we multiply x both sides. Okay, we have this, and then differentiate again, and then multiply by x again. Okay, you all have some complicated polynomial on the left side, but the great thing about it is it's independent of n, because when you differentiate, you drop n, so you just multiply by n. Okay, so you'll have a long expression on this side, but it's a shorter sum than this. Okay, especially if m is small, it will be a shorter sum. If you do it m times, you'll get something like this. Let's say you have done everything on the left side, you'll end up with something like this. And then finally, you can just substitute 1 for x. Okay? So you'll get the sum that we're looking for. And the complexity depends on the size of the expression you're getting from the left-hand side. How long do you think that gets?
M. Each time we keep splitting like multiplication rule, so maybe n term.
Maybe
m.
m.
M square.
Yeah, it makes sense that it's growing in O of m time, although that's not a proof. It just makes sense. Okay. Of course, you can possibly prove if we actually do the operations. But still, if you have some expression of this length and you keep differentiating it, you have to take this amount of time as well to get the new expression. So it will take this amount of time. But I want something faster.
Or else one more thing, like we can take that summation, write nck as n by k, that form. Then like again we adjust that k term there. Now it will be k power m minus 1, right? If we cancel a k without binomial thing, just solve by like summations, the above expression.
Which one? This one?
We can write as n by k into n minus 1 choose k minus 1.
This one?
Yes. We write it just summation n by k into n choose n minus 1 n by k n by k. That's not k equal to. Just write it as summation k equal to 0 to n by k n by k
Divide?
by k into n minus 1 choose k minus 1.
Something like that?
K power m. Now we cancel an m. It will be k power m minus 1 now. We can remove a k.
Okay.
Then now we need to adjust, so we write that k as k minus 1 plus 1, then expand it.
Okay.
Again we get it to k minus 1 form. Other one will be a simple summation, like others will also come out same.
So how do you get exactly from here?
We remove a k.
So we adjust. Let's say we adjust k one time larger. So this will now be n from 0 to n minus 1. N minus 1 choose k, and this will be k plus 1 raised to m.
So we split. We can expand that.
Oh, actually this is minus 1.
Yes.
And then you expand this, and then
Again, like we have similar forms now.
so
Each time the power is decreasing.
okay, so you have
This is also O of m square, but
something like that, and then you have a lot of sums. So this is m squared.
yeah,
Still.
same.
Okay, that's another way of doing that. Okay, but it's still slow. Okay? Okay, so let's leave that for now. Yes?
I had a doubt in the previous solution. So you said that I had a doubt in the previous solution. You said that what would be the complexity of that
Yes, that differentiation one.
Okay, so you differentiate this
And then multiply by x
and then multiply by x.
So
When you differentiate, okay, let's try it, okay? So of course it's not gonna be big, but we multiply by x, and that's the problem. Now you wanna differentiate this, you'll have two terms now.
so every time I think the terms would be doubled.
Yeah, it's possible. But remember that the exponents will be on the range from n minus 1 to, let's say, n minus k, where k is the number of times you have done the operation. Okay, so it will, yeah, it looks like it will double. Let's say we do the operations. Okay, so this is the next derivative. And then we multiply by x. Now look, you have two terms. The next one, there will be two terms from this, but two terms for this, but two of those will combine into one. So you'll have just three terms. And then the next one will have four terms. Okay?
And in that last problem, I think you meant something else, and by mistake you have written something else, because this problem is quite easy.
Which one? This
last one.
Why is it easy?
Do we have to like just find the closed expression, or find it by PNC only, like combinatorics only?
I want some expression without sums, but it's okay to have powers, binomial coefficients. Okay?
We can simplify that.
Yeah,
inner bracket.
You're correct. There's a mistake here. This one, yeah, you're right. So let me check. Okay, so the mistake is, this is I, but this should be N. Now it's hard. Okay? Okay? This one's pretty easy. Okay. Let's proceed. Now let's recall one of the theorems we used earlier. It's called Fermat's little theorem. What does it say? It says that if p is prime and a is some integer, then this congruence holds. Okay? So there are multiple proofs. One of them is, I think that I discussed that last year. You take the numbers 1 to p minus 1, and also a, 2a, 3a, up to p minus 1a. Okay? And then multiply them together. And note that this is a permutation of this, modulo p. So they have the same product. So you have p minus 1 factorial is a raised to p minus 1 times p minus 1 factorial. The factorials cancel out. Okay, that's a simple proof. But there's also a neat double counting proof of this fact. So I'll present it. So how do you count something? But this is a congruence. So we can do that by rewriting this as something like this. Okay, notice that these are equivalent. But now we have an equality instead of a congruence. And we can now try to prove this using a combinatorial argument. Okay? So what are we counting exactly? So what we're counting is, given P cells, we want to color each of them with up to A colors. Okay? There are no restrictions on neighbors, so they can have same or different colors. So that's what we're counting. And clearly, the answer is A raised to P, because you have A choices for each cell. Okay? But how do you count it in another way? Okay, we tackled a similar problem in a previous session. What we do is we first form a ring. Okay, it's a ring of P elements. And now when coloring such a ring, we want to say that rotations are not distinct. Okay, if you can transform one ring to another using rotations, then we don't count them as distinct. Okay? How do you count those? Okay? If you're trying to count those, you have to count the primitive rings first. Okay? Just like before we tried to count primitive rings, we can do that as well here. Okay? But in this case, P is prime, which means the only non-primitive rings are those which can be rotated by 1 to get the same ring. But if that's the case, then all the cells will have the same color. Okay? So it means the only non-primitive rings are those with all the same colors in all cells. And how many of those are there? There is exactly A, one for each color. Okay? And everything else, the primitive rings, for each such rotation, you can form a coloring of this. And it will be distinct since it is primitive. So for each coloring of this, let's say there are K colorings, then you can form P colorings of the line. That's why you have KP here. Okay, so that's a double counting proof of this identity. Yes? Can I what? Can I repeat? Okay. So what we're counting is the number of colorings of a line of P cells with A selections of colors. So clearly the answer is A raised to P. But we can count it in another way by getting a ring and then choosing some rotation of it and then placing it here. Okay? However, we can always choose any rotation because in some rings, there's only fewer than P rotations that give a distinct coloring. Okay? If the ring is primitive, then you have P rotations. But if not, then you might have fewer rotations. But since P is prime, its only divisors are 1 and P. So the only non-primitive rings are those which, if you rotate by 1, you get the same ring. But that means everything has the same color. Okay? How many of those are there? There are A. Now, how about the remaining rings? Let's say there are K primitive rings. For each primitive ring, we can choose one of its P rotations and then place it there as a coloring. Right? So how many colorings are there? KP in total. Okay? P for each primitive ring. That's why we get this. Okay? This one is equal to this plus this for some K. And in fact, we get a formula for K. Right? something like this. This is the number of colorings, primitive colorings of a ring of P elements. Yes?
That part, how you got A into,
Okay, so how did I get this?
how you got A,
I'm saying that this statement is equivalent to this statement because of the definition of mod, right? If two things are congruent mod P, it means...
the combinatorial argument about that A.
Okay, for the third time. So you have a ring of P elements. The first way of counting the number of colorings of P cells is just to choose the colors of each cell. Another is to first start with the ring and then choose some rotation of it and then place it here. Okay? But you cannot just choose any rotation because for some rings, there are fewer rotations that give a distinct coloring. Okay? So, if the ring is primitive, it means all its rotations are distinct. It will give you P colorings of the cells. But if it's not primitive, then you will get fewer. Okay? But remember that the minimal rotation you need is always a divisor of P. And then P is prime, so there's only two divisors, 1 and P. But if the minimal rotation is 1, it means all the cells have the same color. Okay? Is that clear now? Anyone else have questions on this? Okay. Now let's move on to another example. Let's start with the classic one. So let's say there are 6 people, okay? And for each pair of those people, they're either friends or enemies. So you will form some graph. You can form some graph where each edge you can either say they're friends or they're enemies. And the classic problem is to prove that there exist 3 people who are all pairwise enemies or pairwise friends.
So we take any one person, we see that there are 5 edges connecting to other people. So since we have 2 colors, say by friendship we mean red and by enmity we mean blue. So 2 colors and 5 nodes. So by the pigeonhole principle, some color will have at least 3 nodes will be of same color. So now let they go to A, B and C. So like if AB is a red node, then we are done. If BC is the red node, then we are done. If CI is red, then also we are done. So all of them have to be blue. But if all of them are blue, then they form a group of same relationship and then we are done.
Okay, so he gave a classic proof of this, which is first ignore friends and enemies. Let's say we color the edges red or blue, and now we want to find a triangle of the same colors. And the idea is to look at one person, and then there are 5 neighbors. Okay, so there are 5 neighbors. By the pigeonhole principle, there will be 3 of those edges which has the same color. Okay. because if there are only 2 blue and 2 red, so the remaining one has to be either blue or red. Okay? So there has to be at least one color that appears at least 3 times. Now let's look at those people. If any of these edges are of the same color as this, let's say this is blue. If one of these is blue, then you can form a triangle with those. But if all of them are red, then they themselves form the triangle. Okay? So that completes the proof. And I would like to extend this result by a little bit. This is the classic Ramsey numbers. Okay? It says that this result in particular says that if you want to find a triangle of red color or blue color, then you need at most 6 nodes. Because if you have 6 nodes, then you can always find. Okay? With another proof, you can actually show that this is a strict equality because you can find a graph of 5 nodes which does not contain a triangle of the same color. And it's very easy to construct, I think. So it's something like this, and then you color the inner edges with a different color. You cannot find a triangle here with the same color. Okay? And now, the idea is I want to extend this result to something more general. Let's say I want to find a clique of size m. What that means is a set of m nodes and all the edges between them have a red color, or a set of n nodes and all of the edges in them have a color blue. Okay? So we won't try to compute this number exactly, but we can show that it is finite, okay? Because it's not clear why. Okay? In this case, it looks like it's finite, but maybe if you are trying to look for large cliques, maybe for every sufficiently large graph, you can still find a coloring which does not contain either of those cliques. Okay? So how do we do that? One thing we can do is to bound this number with a finite value. Okay? We can do that inductively. Okay? So on the size m plus n, let's say we have shown that this value is finite if the sum is less than m plus n. We want to show that this is finite as well for 2 numbers of size m plus n. Okay? And this is basically an extension of the same argument, except we are not looking at triangles anymore, but cliques, so we have to be a little more careful. And the bound will actually be this expression. Okay, remember that these 2 numbers have a smaller sum, and by induction, we know that this value is finite. So their sum will also be finite, and therefore this one will be finite. So how do we do that? We want to construct a graph of this size such that it always contains either a clique of size m or a clique of size n. Okay, and as I said, it's just an extension of the original one. So I'll just give it directly. So what do we do? What we can do is, in the previous version, we looked at one element or one node. We can also do that. Let's look at one node. And then we group those edges by color and then use the pigeonhole principle. We can do that as well. Let's say these are the red edges and then these are the blue edges. Remember that the size of the whole graph is this. Okay? So how many edges are there in total? Of course, this minus 1, right? So can we guarantee some number of colors appearing at least some number of times? Yes, right? We can either say that let's say these are the red colors and then these are the blue colors. Either there are at least r of m minus 1 n red colors or r m n minus 1 blue colors. There cannot be less than this on both, because if there are less, then there are some will be strictly less than this. Okay? So let's try both cases. I hope I didn't swap them. Let's assume that there are at least this many red edges. Okay? Now, by induction, there are this many nodes here. So there is either a clique of m minus 1 size of color red or a clique of n size of color blue. If that's true, then the property holds. We have found a clique of size n of color blue. But if this is true, we have a smaller clique, but we can add this node because everything is red. So we have found a clique of a red clique of size m. And a very similar thing happens on the other case. Therefore, we have proven this inequality. Okay? The nice thing about this inequality is, remember the path on a grid problem that we tackled? It also has this recurrence. Except there's equals here instead of less than equals. And then the base case will be something like this. Right? Now, in this case, we can easily prove that these are true as well. Since if you want to find a clique of size 1, then it automatically holds true, right? You just need a graph of one node. Okay? Using this base cases and this inequality, you can actually inductively prove that this number has an upper bound of this number if you adjust properly. Okay? Remember that f of mn is m plus n choose m, right? What? Okay, so if you're trying to build the table for f, then you're going to have something like this. And then we're trying to build this using the sum of this. R will be something like that as well, except we're offset a little bit. And then this is actually less than equal. So we were not actually just adding the numbers. It might be less than that. Okay? But this gives us an upper bound. And if you adjust properly, you can actually show that an upper bound for this is m plus n minus 2 choose m minus 1. Okay? So this gives us an explicit bound on the Ramsey numbers. Okay? So for this session, we will end this session with just another example, a problem. I'll give you another problem. And I won't give the solution in this session. We'll try to solve it in another session, okay? So this is the problem. You have a grid. The grid is not necessarily a square, so it's m by n. And in each cell, it will contain either a 1 or a 0. Okay? And you have a constraint that for each 3 by 3 subgrid, there are exactly 2 1s in that subgrid for each one of these. The question is, given m and n, how many such grids are there? Okay, so for example, if m equals n equals 3, what's the answer for this? So what's the answer for this case? Yes? Yeah, so there's only one grid, 3 by 3 subgrid, and there's exactly two ones, so you just have to choose the positions of those. So there's 9 positions, so it's just 9 choose 2. Or 36, right? So in the sample input, you're actually given another case. For this case, the answer is 78. Okay, so the general question is given m and n. What's the answer? The constraints in the problem are this. Okay, so I'll give you a few moments to think. Test. It's okay. Okay. Yes? What?
To solve that problem,
In what?
that square problem,
Okay.
one idea to solve it.
Okay.
The main problem we get is this. So we need to solve this right till some random. I think we can solve this by 1 by 1 minus x power minus 1. So that kind of forms.
By what? I didn't get it.
We want to abruptly stop at some coefficient, so we can get such forms by like maybe Vandermonde second identity, or I don't remember exactly what. Or
Under 1 second?
Vandermonde second, I don't remember, like I saw number. Or
Okay.
else, like we can do like write the big series, then we get some terms like exactly this thing. No, like can we do that?
I don't know.
Okay, it's not the intended.
I don't know, actually. Maybe there are multiple approaches, but
Okay.
I'm looking for a formula, not just a way to compute. Okay? Okay, any ideas? Yes? Okay, so as I said, we won't solve this problem in this session. So we'll probably leave a hint or two, and then leave the full problem for you to solve. I'll leave the link. Okay. So the hint in these kinds of problems is, of course, going to be hard. There are multiple approaches, but when solving these kinds of problems, it seems tough because there seems to be no pattern, or you cannot derive a simple formula for it, right? But the idea is try simplifying the problem first. Okay, in many problems, that's an important step. Okay, so let's say you're trying to solve something for general graphs. Okay, and there's some problem and you can solve. Let's try solving it first for bipartite graphs or planar graphs or something like the edge weights will be 1 or 2 first, something like that. Whenever you try to find some problem and you can't seem to solve it, try to solve a simpler version first, because you need to solve that version first before you solve the whole thing. Right? For example, for trees, a good way is to first look at lines. If you can solve it in a line, then it might give you some insights, and you have to solve it in a line anyway, right? In this case, what can we do to simplify the problem? The what? That's one. We can solve it for a 3 cross M grid. Okay, so something of this size, 3 by M, 3 by N, let's say 3 by N. Okay, this is easier, and that's good. Anything you can get from this? Yeah, you can do DP, so that's fine. Now, what's the next step? You try 4 by N, right? What happens with 4 by N? Can you do DP? You still can do DP, right? Although the states will be bigger, right? Of course, you can do the same thing for larger and larger heights, but the number of states is going to be large. Because basically, you're trying to store the state of the previous 2 columns to know the state of the following one. Okay, for the small heights, there are just a few of those, especially given also the requirement that for every 3 by 3 grid, there are only 2 ones. So there are very few states. But the size of M and N are not amenable for that approach, amenable to that approach. Yes?
We keep the dimensions as the number of ones in each row, right? Here.
What?
In this TP, we
Yes.
keep the dimension as the number of ones in each row.
Yes. For 3 by N, yes. You just keep the number of ones in the previous 2 columns, something like that. You don't have to know their position. But if you go 4 by N, there's something else. You have to know if it is this or this or this. Actually, these two will be the same, but there's still 2 states. Okay? And if you go more, there are more states. So that's good. You have simplified the problem. But actually, there's another way to simplify the problem. And I'm going to give it to you now. Instead of trying to solve this problem, let's try to solve another problem in which we want every 3 by 3 subgrid to have exactly 1 instead of 2. That's much simpler. It's not a subproblem of this problem, but it's much simpler. And in fact, we can simplify even more. Try, instead of 3 by 3, look at 2 by 2 subgrids. Okay, that's probably a very simple version of the problem. So try solving that. Okay? So to recap, we're trying to solve a simpler problem. Every 2 by 2 subgrid must have exactly 1, 1. Yes?
Consider subproblem like where you are considering 2 cross 2 grids, 2 cross 2 subgrids, and you have to have exactly 1 1 in them. Then that would imply essentially that in the final grid, whenever you have a 1, it's surrounded by all zeros. And something like that.
Okay, so you said in the subproblem, if you have a 1, then it will be surrounded by zeros, and that's true. So how many such grids are there? Okay, so any ideas? Let's give you something to start with. Suppose we're trying to build a valid grid. Now we want to try to place the ones. Let's first look at where to place the one in this subgrid, because there will be exactly one. Okay? Let's say we place it here. What does this imply? The cells around it will be zeros, of course. Let's represent zeros with dots. Now, let's try to look at this subgrid. Of course, this will be zeros. And now what about this subgrid? The next one. What? Look at this subgrid. So what do we get when we do that? There's exactly one here, right? But we don't know where. So let's just choose for now. Let's say this. And then this will be zeros as well. And then let's say, then there's also one here. Let's say this one. And then let's say we choose again. And let's do that for the first two rows. So we'll get something like this, where there will be one in every second column. Now what do we do? Let's look at these. What about this square? And this square? In this square, of course, everything else should be 0, right? But this square should have a 1. So this will be a 1. And so this will all be zeros. But this square should have a 1. So this will be 1. Let's try continuing. So this will be zeros, but this should have a 1. This should be zeros, but this should have a 1. So you're basically forced to build these two columns like this. It will be alternating until the end, or something like that. So you're going to do the same here. So it's going to be something like that as well, right? And then notice this column. In this square, everything else must be zeros. So this will be 0, and then this will be 0 as well. In fact, everything else will be 0 here, because there are ones in every other place in the right column. Now, since these are all zeros, you're also forced to alternate this. And you're forced to make everything else 0 here. And then you're forced to alternate this as well. Even though they're the same this time, you still have to alternate, because everything else is 0 here. And then something like that. So notice that the grid actually has a very regular structure. Okay, it looks like you just choose which parity you want to place ones, and then you have to choose how to place them, right? Of course, you can do it in the other way as well. But can you prove that all valid grids are of that form, either this or something similar horizontal? Right? So we just built the grid. So the only choices we did are here. After choosing the first two rows, we're actually forced to, there's only a unique way to build everything else, right? But there's another catch. Suppose in the initial step, so in this case, we chose different places, but what if we select the same places this time? Then we can't find that column where we're forced to place alternate ones, right? So we can't say anymore that everything else will be uniquely identified. but now they're on the same place. So this row will be forced to have all zeros now because of this row. And then what about the next row? Each of those squares must have exactly 1, 1. So there must be an alternating 1, zeros here. There are 2 ways to do that, but it has to be one of those ways. Okay, so it's going to be something like this, for example. And then all zeros again. And then another one, let's say this one. And so on. So we're actually forced to build a grid that is of a similar form, except we do it horizontally. So something like that. So with a bit more work, you can actually make this a rigorous argument that says that all the valid grids are of this form. You choose either columns and then place ones alternately in those, or rows, right? But do you understand the main point of this construction? First, we chose the first 2 rows, and depending on whether we placed ones off by each other, we either get a column-based pattern or a row-based pattern. Okay? Now, how to count them? Okay, let's try to count such grids. So let's count the kinds separately. So let's say this is n by m. Let's try to count this. This is very similar. Okay, so the formula we get for this will be the formula for that with n and m swapped. Okay, so how do we count the number of grids of this form? Of course, we select first the columns which will contain the ones. There are only 2 ways to select those columns, either the even numbered ones or the odd numbered ones. So that's 2 possibilities. No, actually, those 2 kinds will not have the same counts. So let's try both separately. Let's say the even numbered ones first. So there are n columns. So now, how many of those are there? First, count how many of the columns are we placing ones? So there are floor of n over 2. Is that right? Or ceiling? Floor, right? So these are the number of columns. And for each column, how many choices are there? 2, right? So we have the formula 2 raised to n over 2. And then the other case, odd numbered columns. Ceiling this time. And then there are still 2 choices for each. So we have something like this, right? So we get this formula independent of m. But for the other case, it's the same formula except we swap n and m. So we get a very similar formula. Do you think that's correct now? No? Yes? What? Yes. There are some grids that are counted multiple times. Some grids actually look like something formed from this process or this process. But how many such grids are there? 4. Why 4? Of course, the idea is you want each column to have alternate ones and each row. But if you have some 1 here, you're actually forced to build that row uniquely in the column. And then the next row are built uniquely as well. And actually, you'll get a very regular grid where the distances between the ones are 2 columns or 2 rows away from each other, right? And so there are just 4 choices, depending on where the first one is. So we subtract 4. And now we have a formula for the simpler problem. And it's very simple. So that's the hint for you. We solved it for 2 by 2. Can you extend it for 3 by 3? And there's only 1 in each 3 by 3 subgrid. And then if you solve that version as well, maybe you can solve it for 4 by 4 if you want. Or you can approach the main problem, which is we want 3 by 3 subgrids to have exactly 2 ones. Okay, so I'll leave that full version to you. I'll leave the link as well so you can submit your ideas. these are the constraints. So we can now take a break for a while. We'll continue the lecture later.